Lecture 11 is going to cover numerical solutions to transient problems. So last time we went through a few steps just to understand what 1D transient problems look like, how we characterize them, and how we can describe them in kind of approximate terms. So we derived this thermal wave depth equation, which is delta t is approximately equal to 2 times the square root of alpha t. So this equation gives us an estimate of the depth that a thermal wave can penetrate given a certain amount of time t. Alpha is the thermal diffusivity, which is a property of the material. So again, this is an approximate model because we developed it using this idea of an approximate thermal resistance between the surface of the domain and the end of the thermal wave. And we made some kind of linear approximations in doing that. The diffusive time constant quantifies the amount of time that it takes for internal equilibrium to be achieved. So what this means is if there's a disturbance in the surface temperature or disturbance in the surroundings, the amount of time that it takes for that for the internal conduction problem to kind of settle down is described by tau diff. The governing partial differential equation for 1D transient conduction was something that we derived. So we went through, did a control volume analysis, and came up with this equation here where we're saying it's alpha times the relationship with temperature and time and the coordinate x. This problem, as I mentioned, is hard to solve, or there's techniques to do it, but it's kind of beyond this class. So I gave you some solutions to this. What we'll end up doing now is look through how we actually solve transient problems using numerical techniques. But for the meantime, if you know the boundary conditions, right, you can match the boundary conditions to your problem. Then you can go back and use one of these existing solutions and just kind of apply it. So the bottom line here is that we need to be comfortable with numerical solutions. We need to know how those are going to work, and we need to be able to apply it to the transient problems. So today we're gonna start off by talking through 0D transient problems. Again, we're going to go back to this kind of simpler, only time-dependent problem. We're not going to allow any spatial dependence in temperature. And then we'll develop numerical techniques for this type of problem, the simpler type of problem, and eventually apply them to the 1D scenarios as well. So if you remember back, we have for our 0D problem, right? We have some control volume that surrounds the entire body, and that's making the assumption inside our control volume that the temperature is uniform. The temperature will change as a function of time, and it responds to conditions around it. The governing differential equation for this is given here, where we have the rate of change of temperature with respect to time is related to both the current temperature. This is the current temperature of the body, and this is the temperature of the surroundings. Tau LC is our lump capacitance time constant. That includes things like the resistance to the surroundings, the mass of the object, and so on. So the important thing to note here is if we know the current temperature of the body and we know the temperature of the surroundings and these geometric and heat transfer parameters, we can compute the rate of change dt with respect to time. This is really important, right? So this gives us basically, we make this following observation. dt is some function of the current temperature and of time. So this is something that we call a state equation. Right, a state equation is an equation that relates time, that's time rate of change, of a variable. In this case, that's temperature, to the system state. Right, by state, I mean the current temperature. So it relates the time rate of change, dt dt, to the system state, which is the current temperature and the current time. So how do we deal with this from like a numerical standpoint? Well, what we're trying to do is basically come up with an equation that estimates this dt dt, and then use that dt dt, this slope, this gradient, to step forward or like extrapolate forward in time. So what we're going to do is, just like the other problems, we're going to start by discretizing. Discretize the time domain. And so we would do that. We'd say time is going to be between 0, t. Time is between 0 and what we'll call t sim, which is the total amount of time that we're interested in simulating. So we're going to break this into n steps, which means that delta t, the time step, is equal to t sim divided by something related to n. In this case, we're going to have our first discretization at time equals 0, and our last discretization at the end of the time simulation. So again, we're going to have n minus 1 segments or steps that we're trying to estimate. So then we'd say, just in mathematical notation, we're going to say the time at index j, right? J is the index. Let's just use j because we've used I for spatial indexing. So j is going to be j minus 1 times delta t for all j in the set from 1 to n. We have in this differential equation, this differential equation over here, we have one derivative. It's a first order differential equation. So we only actually need one boundary condition to solve this. The boundary condition for us is going to be the initial temperature. For this problem, let's say that initial temperature is T initial. But importantly, how are we enforcing the initial temperature? Well, we can develop an equation that lets us predict, say, T2, T3, T4, the next temperature. We just need to specify in a separate equation T1. So we would actually, in ease or however we're solving this, write an equation that says T1 is equal to T initial. And then we'd write a separate equation for what T2 is and how we sort of get to that point. So let's go through then and figure out how we move from T1 to T2, assuming we've already specified T1 as T initial. And this is the entire basis of the numerical method.